Welcome to our lesson on Doppler effect, and we're going to look at the Doppler effect in sound and the Doppler effect and light. So, first of all, what is the Doppler effect? Well, Doppler effect is the apparent change in the frequency of a wave when there's relative motion, all right, between the source of the wave and the observer. So there's two things that are important here. Number one, it is an apparent change. The frequency of light or a wave cannot change unless the source's frequency actually changes, but you are observing a frequency change. The second thing is that there needs to be motion. So either the source of the wave is moving or the observer is moving, though sometimes in the real world that means both is moving. But we're just going to look at what happens when one moves. What we have to remember is that the pitch of the sound is related to the wave's frequency. Okay, so often when we talk about pitch and frequency in this section, we're talking about the same thing, though frequency is a much better word to use. The definition of frequency is that it is the number of wavefronts that pass a given point in 1 second. We're actually going to consider the fact that we can change this part. Okay, that is what's going to change, the number of wavefronts. The higher the frequency, the higher the pitch. That's not loudness, that's the tone. So like a soprano singer has a very high-pitched voice, okay, which can be a little annoying, and a baritone or a bass singer has a very low-pitched tone, okay? So the pitch of the sound is how high or how deep it sounds. It is not about the loudness. We're not concerned with loudness here at all. So, if we consider a stationary object, now in this case, what we have here, this little red dot, that is my listener. The black dot is the source, whatever that source may be, an ambulance, a whistle, a train, an aeroplane, doesn't matter. When it emits sound, those sound waves travel out at a regular intervals, okay, because it has a regular frequency. Those intervals are the same everywhere, and sound is three-dimensional. So even though my listener is over here, the sound goes in all directions. What's important is that it travels at the same speed in all directions. Now, speed of sound isn't like the speed of light, which is a constant 3 times 10 to the 8. The speed of sound depends on the medium that it's traveling through, be it a gas, a liquid, or a solid. Also, it depends on the temperature of that medium. So, for us, we usually use the speed of sound in air to be anything between 330 to 343 meters per second. That has to be given to you in the question somewhere, or you work it out depending on what they give you. The distance between any two crests, so the lines or the crests or the compressions, okay, is the same for all of these, and my observer over here hears exactly the same frequency, the same pitch as the source for this moment, okay? We're not concerned about loudness, so at the moment they're hearing the same sound, they're hearing the same pitch, the same frequency. Now what happens is if the object is moving towards the source, or all the source is moving towards the object, doesn't actually matter, what happens is the source makes a wave. Okay, let's change this to this. So the source makes a wave, then, like one of these, then travels a little forward and makes another wave. So the source creates the waves at the same rate, but it catches up to its waves. Now what that means is in front of the source, the compressions get closer. If the compressions get closer, then the observer experiences more wavefronts per second. More wavefronts mean increase in frequency. It's an experience. It's not a true change in frequency, but you will experience it. And remember, for us as humans, when we hear sound, we're hearing our eardrums are vibrating. As our eardrums vibrate, that is the frequency at which they vibrate is the sound we hear. So if we're experiencing more wavefronts per second, we're going to hear a higher frequency. Okay? If we're moving away now, so what happens here is the object creates the sound, moves away, and then creates the second one. So now it's moving away from the wavefronts that it's creating. So the distance between the crests gets bigger. So now we experience fewer wavefronts per second. What does that mean? We have a decrease in frequency. Okay? All of these are related to the fact that we need to have a constant velocity. We're not going to look at what happens when the velocity is constantly changing, so if there's an acceleration, because that involves calculus. Alright, so that gets us to the equation. Now, this equation doesn't look like it's nice, but it actually isn't so bad. So what does the equation tell us? The frequency of the listener, that the listener observes or hears, whatever that listener may be. So this could be a person, it could be a device of some sort, it doesn't matter. Okay? This here, that bracket is the important one because that shows the relationship. V is the speed of sound, which they need to give you. Here we're going to plus or minus the listener's velocity or the source's velocity, depending on the motion. And the important thing to remember with this equation is it's all determined by whether we know the frequency must increase or decrease. Vs is then the frequency of the source, whatever that source may be, a car, a police van, an ambulance, whatever. Okay? Important, we're working in meters per second and frequencies in hertz. For our curriculum, either the source or the listener must be stationary. Okay? They must be stationary. So, we'll look at equations at the end of the video. Now, oopsie, there we go. What we need to realize is we can apply the Doppler effect in medicine. It's got a very good use in medicine. When it comes to medicine, we use it in what we call Doppler flow meters. It's used to measure how fast blood is moving through veins. It's also used to measure the heartbeat of the fetus of a baby. What happens, okay, is the transmitter sends down, I'm not sure you can see that, sends down an ultrasound, a very, very high-pitched sound, which then gets reflected back off the baby's heart, blood vessel, whatever the case may be, and then it looks at the receiver. The difference in those two frequencies is then put into a machine, which then sends out what the velocity of the object it was measuring is moving at. So this is a good way to look at whether a patient needs heart surgery, whether there's an issue with their veins, whether the rate at which a baby's heart is moving. So it's nice and easy, and it's non-invasive, so it's safer. Okay, so let's look at these examples. The important thing in our examples is to work out what information goes where. So, a police car races towards an accident scene at 25 meters per second. The siren of the police car emits a sound of 700 hertz. So straight away what we're being told is that the source is moving at 25 meters per second, and the source is emitting a frequency of 700 hertz. Then they ask you, what is the frequency of the sound? So now this is the listener that's heard by the people at the accident scene. So the listeners aren't moving. We're going to assume for this question that V is 340 meters per second. Okay? So it's going towards the people. So VL must be bigger than FS, sorry, not V. So my source is going to be, oopsie, not what I wanted to do. Give me a second, there we go. So there's my frequency, V plus or minus VL, V plus or minus VS over VS. Okay, and that should be VL over here, not VS. Okay, that's an L. That's what I'm looking for. So, if we work backwards, VS is 700. That was easy. My listener isn't moving, so its velocity is 0. So that means that all I have at the top of my equation of my fraction is 340. At the bottom, I know I'm going to have 340 and I'm going to have 25. Now it's a decision as to whether I'm going to plus the 25 or minus the 25. I know that VL must be bigger than VS. That means my fraction must be bigger than 1 so that I get a bigger value. I then minus the 25 so that I have a big number over a small number. So then we plug this into our calculators and we're happy. Okay? Oh, no. Only if we write it down correctly. So that's 5-6 hertz. Straightforward. Then, now they tell you a siren emits a frequency. So this is my source's frequency. Frequency of my source is 440 hertz. While a car drives away from the siren, the driver hears the siren. So that's my listener of 400 hertz. And then they want to know what the car's speed is. So the car, who is the listener, is moving away. The source is then stationary. And once again, I'm going to take the speed of sound as being 340. So we start with the equation, because that's always going to be the same. I've done it again. So let's do that. That's VL. We know that that's 400. We know that's 440. And here, we know that the source wasn't moving. So the bottom's going to be 340. And here we go. That's not helping either. Let's take that out. And there we go. Let's do it again. Doesn't want to come off. There we go. All right. So that's 340 and that's the listener. We know that the frequency has to get lower. So in my fraction, the small number has to be at the top, the big number at the bottom. So I'm going to minus VL. Now it's a maths problem. You guys can work that out. That gives me 30.91 meters per second. Straightforward. Now, just quickly, this is Doppler in terms of sound, but Doppler works with light as well. Okay, so it's fairly straightforward. The important thing to remember here is that Doppler is characteristic of all waves. Transverse, longitudinal, doesn't matter. With sound, we hear a change in pitch. With light, we see a change in color. Why this is important for us is it gives us insights as to what's happening with our universe. So, a star, such as the sun, emits waves into space. We know that's why we can see light. Okay, these waves are electromagnetic radiation. There's the whole spectrum of magnetic radiation. And this would happen with the whole spectrum, but we can only observe the color one physically. So there's a whole bunch of frequencies here. Now, we know that when it comes to the spectrum of color specifically, so we're looking at the visible light, which goes from red to violet. Red, very important to know, longest wavelength, smallest frequency. Violet, shortest wavelength, highest frequency. Remember, they're the inverse of each other because they're all traveling at the same speed. So, what does this mean? If we could see a light source, or we could travel close to the speed of light, and we were looking at a wave source, if we're going towards the wave source, we will see the frequency increase. Okay, same as with sound, the frequency would increase. What does that mean? We would see blue light. If we could move away from a source close to the speed of sound, we would see a decrease in frequency, so we would see red light. In everyday situations, we can't experience this because we can't travel close to the speed of light. Okay, that's the problem. Going at 20 meters per second makes no difference to what color we see. Why is this important? So now we have to go back a little bit. When we take light and we put it through a prism, it breaks up into the colors of the rainbow. put it through a spectroscope, which is just it looks like a miniature telescope basically, with a very fine slit in it, and it allows light to break up, okay, because the light waves diffract, they move at angles through it. This gives us a continuous spectrum, all the colors of the rainbow. You can't see one from the other. You can't see exactly where it changes from orange to yellow to red. It's a continuous spectrum. All the colors are there. Now when we pass light through a gas, okay, that gas absorbs some of it. So if we take white light and pass it through hydrogen gas, we get what is known as an absorption spectrum. So this is white light passed through hydrogen gas, essentially, okay? And what happens is certain colors get absorbed. They're missing. We're not going to worry too much about how that happens exactly, but they're missing. Hydrogen gas will always give us this pattern. It is unique. It's like the gas's DNA. It's how we can identify elements. Every element gives us a very specific absorption spectrum. So, what that means is when scientists look at stars, they can see what gases are made up of the stars, looking at what they know from our sun. So, what happens is this, is looking at what we know from our sun is mainly made up of hydrogen, because that's the absorption spectrum we get. So there's a little bit of a leap here where we go, well, if our sun is that, then all the stars we see must be that. So stars emit light. Our galaxy which is the Milky Way, is made up of millions and millions and millions of these stars. Edward Hubble, very important astronomer for us, observed, and this was a long time ago, 100 years ago, how the spectra from these distant galaxies worked and how they changed. This was a major breakthrough for science, okay? So this is what they saw. They looked at the absorption spectrums, and here we've got a whole bunch. So in the lab, this is the absorption spectrum we get from hydrogen. When they look at a nearby star, and I'm not talking about the sun, this is just another nearby star, what they see is the black lines, okay, have the same pattern, so they're the same distance apart, but they've moved. They've all moved, if you look carefully, to the right. So they've moved towards the red. The further away the galaxy is, the further away the star is, the more pronounced the shift is. Now, the more pronounced the shift is means that they're moving faster, but it's gone to the red side. That means frequency has decreased, the wavelengths are getting bigger, so it's moving away from us. It's known as redshift. That redshift, okay, is the shift, this is the definition, there's a spectra of distant galaxies towards longer wavelengths, and what it means for us is a couple of things. One, the further away they are, the faster they're moving. Two, it suggests, doesn't prove, that the universe is expanding. Scientists then went, well, if all the stars are moving away from us, at one point they must have been closer together, which then gives us a starting point for what we call the Big Bang Theory, okay? Where everything started as a small, hot, dense mush of things. It exploded, and then our universe started to expand. Okay, it doesn't completely prove it. It just gives us evidence that it was there. And hopefully that has helped. See you next time.